Electronic Circuits, lecture number 10. We were resuming module number 1.2, that is bipolar junction transistor. And in this module, we have covered BJT construction, working, and yesterday we have covered input-output characteristics. Today, we will be going through the concepts of DC load line and the concept of biasing. Okay, let me see if anyone has joined. Yeah. Please keep your yeah. Okay, so we'll continue with the concept of DC load line and the concept of biasing. So let's begin. So you all can write along with me. The first topic, the concept we'll be going to discuss today is transistor biasing. What do you mean by transistor biasing? We'll try to understand. Transistor biasing for bipolar junction transistor. So transistor biasing means that we need to establish, please write it down, establishing and maintaining proper collector to emitter voltage, collector to emitter voltage. What is collector to emitter voltage called as? VCE. Okay, collector to emitter terminal voltage and collector current, which is called as IC. Again, this is a terminal current. So transistor biasing means establishing and maintaining proper collector to emitter voltage and collector current in the circuit. All right. Let me check if anyone has joined now. Yeah. Okay. So this is what you mean by transistor biasing. Now let me show you with the help of a symbol. So this is the symbol of a BJT. This is my collector terminal, base terminal, and emitter terminal. And what do you mean by maintaining proper VCE? Means this voltage, terminal voltage VCE, and the current IC, which is flowing into the collector terminal. All right. So establishing and maintaining. Establishing, first of all, you have to properly give the voltages, establish VCE and IC, and then maintain it, okay, throughout the operation of the circuit. That means these values shouldn't be disturbed. Okay, so this is what you mean by transistor biasing. Now, what are the requirements of transistor biasing? We'll see shortly now. What is the need of biasing? Someone has joined. Let me check. All right. So let's check. Let's check the why does the IC and VCE will change. So basically, the collector current IC and VCE can change in a BJT due to the following. So one, due to variation in temperature. So if there is a variation in temperature, the value of IC and VCE will change. Because with increase or decrease in temperature, beta changes. And when beta changes, IC gets disturbed. Similarly, VCE gets disturbed. Second thing is variation in gain. Basically the current gain. So beta actually is a function of temperature. You must have experienced that in your lab also, that beta changes with change in temperature. All right. So next will be your IC and VC can change due to variation in leakage current. Variation in leakage current. What are the leakage currents in a BJT? Yesterday we have seen ICBO and ICEO. These are the leakage currents present in the BJT. So your collector current and collector to emitter voltage can change due to variation in the leakage currents also. Next, variation in the supply voltage. Variation in supply voltages. You remember in common emitter config practical circuit, you were giving two supplies, VCC and VPP. So if there is a faulty power supply, this VCC and this VPP might change. That might lead to changes in IC and VCE. So for a BJT, if you're fixing VCE and IC, they should not change. But they change due to these four factors, which is variation in gain, variation in temperature, variation in leakage currents, and variation in the supply voltages. All right. So y'all are just recapping what is transistor biasing. Transistor biasing is establishing and maintaining proper collector to emitter voltage and collector current in a circuit involving BJT. So in a circuit involving bipolar junction transistor. All right. And it is valid for both NPN and PNP. So it's valid for both NPN and PNP transistors. Okay. So now let's see what is the need of biasing. Now understand why we are studying this topic. So write down next concept is need of biasing. All right. So the very first need of biasing will be, let's check it out. Let's recap it. First, we require a particular value of IC for a transistor. Next, we need a particular value of VP so that it operates in the forward active mode. Then we also require the value of VCE. Okay. So we require to establish and maintain proper values of IC, VB, that is base emitter voltage, and collector emitter voltage. All right. And biasing helps, it helps eliminate need of additional DC supply. Now, what do you mean by it? Additional DC supply. I guess you must have seen the circuit of common emitter configuration, right? I think this was the circuit. Let's draw it quickly. Yes, in general, I mean, in really quick time, this was the circuitry. So basically my focus is these two. I'm not interested in anything else. So this was VPB and this was VCC. So how many power supply you require for changing the input and output? How many external supplies you required here? You require two external supplies. Okay. So in biasing, if you bias the transistor, it will help eliminate the need of additional power supply. So instead of two power supplies, now we will have only one. So here, two DC supply voltages used. Okay. So a biasing, but when we bias the transistor, it will help eliminate the need of additional DC power supply. All right. Now, next point is, I hope the screen is audible and I mean, screen is visible and I am audible. Just one of you can confirm. And the pace is fine. Everyone, you're following. Hello. Just so that I can
Yes, sir.
continue in the same. Okay, good. So now write down the value of IC and VCE is expressed in terms of operating point. or we call it as Q point. So this we are going to observe it today only. We are going to analyze one biasing circuit and we are going to determine where is the Q point. Okay. So the value of IC and VCE is expressed in terms of Q point. So for example, if you find out the value of VCE and IC in a BJT biasing circuit, you need to write it as follows. So Q point, operating point of the BJT will be VCEQ, comma ICQ. Q subscript will be for the operating point or a Q point. Okay. And this is required. This is the mandatory requirement for faithful amplification. So write down for faithful amplification, Q point must be selected properly. What do you mean by that? We'll come to it right away. Q point must be selected carefully. All right. Now, where is this Q point on the characteristics? We'll see now. Okay, can we go to the next point? Yep. So now comes the concept of DC load line. Now comes the concept of what is called as DC load line in a BJT. It is also short form called as DCLL. All right. So let's plot the output characteristics graph of a BJT, NPN BJT in common emitter configuration. So how does the graph looks like? All of you will agree that this is what the graph says, correct? This is the output characteristics in common emitter mode. Yesterday we have only seen, right? Yes or no? Then you have something called as a DC load line, which is plotted in the output characteristics. And the DC load line will look something like this. Here it is. This is called as DC load line. Now, how it is plotted, we will see exactly when we study the biasing circuit. So basically, the intersection of DC load line and the output characteristics graph, this is output characteristics graph, will give me the Q point. So this intersection over here will give me the Q point. So this is my Q point. Okay, now this Q point corresponds to one particular value of VC. If we extend it down over here, this value is called as VCEQ. And if it extends to the y-axis, it is called as correspondingly ICQ. Okay, so that is the Q point. Now this Q point should not be disturbed. All right, because if this Q point shifts over here, shifts above, we have a saturation region over here. Remember, we have saturation over here, and here we have cutoff. So if the Q point shifts to the down, the transistor will operate near the cutoff region, which we don't want. And if the Q point shifts above, it will be near the saturation region. We don't want either. We want it to be in the forward active region. So forward active region will be this portion, majority in between this. You know, in the graph, where is the forward active region, right? So that is what the DC load line is. DC load line gives you information about the location of the Q point. So write down DC load line gives information about the location of Q point. And how do we find Q point? How do we find Q point? Q point is the intersection of DC load line and output characteristics of NPN BJT in common emitter mode. Okay, so what is the Q point? Q point is the intersection of DC load line and output characteristics of NP and BJT. Are you got this point now? Okay, and how do we write Q point? Q point will be for a transistor VCEQ. Q stands for this Q point or ICQ. It has many names also. It is also called as Q point means quiet. Q stands for quotient. Quiet or quiet. It should not change. It should not vary. So this location which I marked over here, this location should not change. And why it changes? Why does the VCQ and ICQ changes? Because of these four reasons which I've written over here. Variation in temperature, change in gain, variation in leakage currents or supply voltages. Okay, someone has joined. Let me check. All right. Okay, let's continue further. So far, any doubts? Anyone? You understood what is a Q point? What is a DC load line? And why the intersection of a DC load line and output characteristics is a Q point. So basically what happens is, let me just show you a little bit better picture. So this Q point might shift. Okay, this Q point might go over here. So let's say you have three kind of a situations here. Okay, in all the three cases, we have output characteristics IC versus VC. This also IC versus VC. Okay, in all the three cases, let me draw the output characteristics. All right. So let me draw this curves. Sorry for that. Okay. And let me draw the Q point, the DC load line for these three curves. Okay. Now the Q point for the first one, the Q point is over here. For the second, the Q point is over here. And for the third case, the Q point is over here. Okay. So tell me in which region of operation this is near saturation. Yes. So Q point is in the closer to y-axis. So it's near saturation. This is in forward active. And this is in near cutoff. Because as I've already told you all before, I think someone has joined. Let me check. Yeah, that's it. Um, okay. All right, let's continue. Forward active region, right? As I've already told you, this will be saturation point and this will be cutoff. So here it is near the cutoff point. So BJT for an amplifier purposes, for a BJT to use as an amplifier, it should operate in the forward active mode only. Then only it will be faithful amplification will happen. So this portion, your operating point should be in this area only. If it is closer to your saturation, this will be near saturation. This portion is forward active and closer to this will be closer to cutoff. Okay, so the location of Q point on the DC load line is important. Ideally, what we want is, ideally, we wish the Q point to be at the center of DC load line. Okay, this is the ideal situation. If it is in the center of DC load line, easily my even if there is a slight variation of Q point my up and down, it's still in the forward active region. and your BJT should stay in the forward active region. All right. So this is the concept of Q point DC load line. Now, any doubts over here? Can someone reply quickly so that I can move on? Any queries? Everything is clear, whatever we have discussed today? Okay. So let's go to the next point. Write down need of stabilization. What do you mean by stabilization? We want stable Q point, meaning we want stable value of VCE and IC. Okay, so if we see the output characteristics again, this is VCE, this is IC. So in DC load line, if this is the Q point, we want stable Q point. So this is VCEQ, ICQ. Okay. So we don't want this Q point to shift either near the saturation or near the cutoff. Okay. So we want to stabilize the Q point. We want a stable Q point. That is a necessity for stabilization. Now, why does the Q point will change? Anyone? Why does the Q point changes or the value of VC or IC will shift? So that means, see, Q point shifting over here. This, let's say it is shifting over here. So what will change? You'll get a new value of ICQ, ICQ dash. You will get a new value of VCQ. We don't want that. It is not preferred to have a new values of VCQ. So Q point should not shift. Okay. So we want the that's why we want the stability of Q point. All right. So what is the need of stability? It means, this means formally, write down, what do you mean by stability? The rate of change of collector current, which is IC, with respect to collector leakage currents, ICO. We generally call it ICO because it is either ICBO or ICCO. So we call it ICO. See, the Q point IC can change due to change in following. First, leakage current ICO. Okay. Second, it can change because of change in beta. Because of change in temperature, beta changes. Third, it can change because of change in VB value also. So we have three types of stabilization. We require three types of stabilizations. One to stabilize leakage current. Then next is the current gain, and next is VB. So need of stabilization is the rate of change of collector current with respect to the leakage current. The most influencing factor is the leakage current. Now, once we are checking the stabilization with respect to one, so let's say if we are studying the stabilization with respect to only leakage current, the other two should remain constant. Okay. So the rate of change of collector current. So how much does the collector current changes uh, with respect to the leakage current ICO at constant beta and VCE is called stability factor. Stability factor, which is determined as, it is denoted as capital S. Okay. So the rate of change of collector current with respect to collector leakage current ICO at constant beta and VC, let's say VC or VBE actually, here it is VBE, is called stability factor. And this stability factor is only with respect to ICO. So we can write S ICO. Some people write it only S also. Okay. And it is will be partial derivative of delta IC divided by uh, change in ICO at beta VB constant. So we are assuming that variation of collector current with respect to beta and VB are constant. It only changes due to leakage current. So please Note this expression down. All right. Okay. Now let's derive the expression for stability factor. So actually the stability factor for ICO is denoted by S or SICO. Stability factor with respect to beta is denoted as S dash or S beta. And stability factor with respect to VB is denoted as S double dash or SVB. You only have a variation with respect to ICO in your syllabus, not the other two. So let's start with and derive the expression for the stability factor due to leakage currents. So write down the question, derive the expression for stability factor SICO or just S. All right. Someone has joined. Let me, yeah. Stability derivation for expression of stability factor. Okay. Do you remember what was the collector current expression given by yesterday? We have written IC is beta IB. There was one more term over here. Can anyone tell me? We'll call this expression number one. IC was beta IB. Yesterday we have introduced the leakage current. So what was it? Anyone? It was 1 plus beta times ICBO, right? So but we'll write in general ICO. So ICO is the leakage current. This is my leakage current. Okay. Now what do we do is we'll differentiate this expression number one with respect to IC. So differentiate equation one with respect to collector current IC. So first will be delta IC divided by delta IC. Okay. Then beta times beta is a constant we are assuming. Delta IB with respect to delta IC plus again 1 plus beta is a constant delta ICO divided by delta IC. All right. So this part will be 1. We are taking this over here. So it will be 1 minus beta times delta IB upon delta IC is equal to 1 plus beta times. Now what is stability factor given by? S is given by delta IC upon delta ICO. So this will be 1 upon S. Agree? Yes. So what will be S now? S will be 1 plus beta in the numerator divided by 1 minus beta times delta IB upon delta IC. So this is a generalized expression for the stability factor. Please note it down. Okay. Or we can denote it as S dash or SICO. Oh, sorry, not S dash, S. Just we can write or SICO. So this is the stability factor where only a leakage current is changing. Okay. So all of you have your calculators with you because we are going to analyze now the various biasing circuits. Have you completed up till here? Can I start? Everyone? Yes or no? Hello. Can someone reply? Can I start this topic? Okay, understood the need of stabilization and the derivation of the stability factor. Everyone clear about it? Numerator is 1 plus beta, denominator is 1 minus beta into delta IB upon delta IC. So if you want to find out the stability factor with respect to leakage current for any biasing circuit, you have to use this formula directly. Okay. Now let's begin with the most important concept. Actually, we have dived into a module number 1.3, that is DC circuit analysis. of BJT. Okay, so we have dived into 1.2, we have completed now. We have dived into 1.3. Let's start with the concept of, let's see the types of BJT biasing circuits. So write down BJT biasing circuits. So what do they do in general? They stabilize, they help us to find out the proper values of IC and VC. Also, the major advantage is it eliminates need of additional power supply. Okay, so remember this BJT in characteristics. If we want to do the characterization of this BJT, that means we want to find input plot, input output characteristics. You require two power supplies over here and over here. Okay, so this requires two external power supplies. So two external supplies were present over here. Okay, so the biasing circuit, the BJT biasing circuit will remove this, the need of two external supply. It eliminates the need of additional power supply. So with one supply only, your BJT circuits will operate. So let's say that what are the types of BJT biasing circuits? So let's write down the types. Number one, fixed bias, fixed bias circuit. And in fixed bias circuit, we have one more category, fixed bias with emitter resistor. That is also called as emitter bias. Okay. Next is collector to base bias. Fixed biasing, we can say collector to base biasing. Here also we have one more category, collector to base bias with RE, with emitter resistor, RE. Okay, collector to base bias with RE. Then there is third, which is most famous. It is called as voltage divider biasing. In some textbooks, they also call it potential divider biasing. All right. So these are the types of biasing circuits. These are the types of BJT biasing circuits. Okay, everyone. So let's draw it quickly. Everyone ready? Okay, so I'm drawing few circuits over here. Please draw along with me. So here it is, the first one. See, if I connect the biasing circuit like this is RC, resistor RC, this is RB, and this is my power supply, VCC. One power supply only. Okay. So next circuit will be, this is RB. This is VCC, RC, RB, and this is ground. Then you have, let me take it a little down. I will name it, just draw the circuits for time being. So we do it like this. We have a collector register. We have emitter terminal register. Then we have a potential divider R1 and R2. All right. This is ground and this will be VCC. So this one is called as fixed bias. This is called as collector to base bias. And this is called as voltage divider bias, the one which we use it for amplifier, voltage divider biasing circuit. Okay. Now, if I add a variation over here, that means if I add a resistor over here in place of this wire RE, then it becomes fixed bias with RE. If I add a resistor over here at the emitter terminal, with between emitter terminal and ground, then it becomes collector to base bias with RE. So these are the primary three biasing circuits. With variation, it becomes phi. Okay, everyone following this? Please complete it fast. If you all have completed, can I move on to the next one? Yes, students. Anyone has any doubt so far? Any queries? Can you give me a quick reply? You all have completed this? Yes or no?
Yes, sir.
Okay. Now, extreme attention, give next 20 minutes or so, give extreme attention because we are going to analyze one biasing circuit. Exactly similarly, the analysis remains same for other biasing circuits. So first of all, let me add if anyone has joined. Yeah. Okay. So let us begin. Write down the first circuit, fixed bias circuit. We are going to use NP and BJT for our analysis. Okay. So first of all, draw this biasing circuit. I'm drawing it over here. So this is plus VCC. Okay. This is RB base resistor. This is collector resistor. And this will go to the ground. Now, when we use this for amplifier purposes, there are some additional connections shown. Here there will be a capacitor and here there will be a capacitor. Right now, it's not a concern. That's why I've drawn it slightly in different color. This is input coupling capacitor. This is output coupling capacitor. This is my AC input, which we apply over here with respect to ground, AC input signal. And here I get AC output signal. Right now, we are only doing DC analysis. So these are not important, but still I have written it over there. Okay. What do you mean by this plus VCC? Plus VCC means we are doing the connections this way. I'm showing in dotted line only once. So this is positive. This is positive. This is negative with respect to ground. And this is the same ground which we are using over here. So it's actually connected over here. This is VCC. If this is connected over here, doesn't mean that it's connected over here also. It's the same. Supply is connected in parallel with this point and ground. Okay, so this really means this because in our circuit analysis, we are not going to again and again draw this. We will just show it by this symbol. Are you getting it? The supply will be henceforth showed as follows. Earlier we used to show it like this, right? We'll show it like this only. Plus. So this means that it's connected plus positive over here and negative above. You can see over here. This is plus, this is negative. All right. I hope it is clear now. Okay. So first thing we write down is we are doing DC analysis. So let's write down DC analysis. Now for DC analysis, for DC, do you agree frequency is zero for a DC? Yes or no? So what will be capacitive reactance? 1 upon 2 pi FC. Can you tell me how much is this? Infinity. Therefore, the capacitors present over here, capacitors CI and CO acts as open circuit because the capacitive reactance is infinity. For DC voltage, frequency is zero, capacitive reactance is infinity. Therefore, these capacitors act as an open circuit. Okay, so we have left out with the circuit only, the main circuit only. All right. Are you following? Yes or no? Okay. Now we'll redraw the circuit without those capacitors. So let's draw it again. So emitter terminal will go to ground. Collector terminal we have a resistor. Base terminal we have a resistor which is connected like this. And this is my VCC plus VCC. Okay. This is RC, RB. Now let me mark terminal voltages. So which are my terminals over here? First of all, this is base, this is collector, and this is emitter. So voltage between base and emitter is VBE. Voltage between collector and emitter is VCE. What about the currents flowing? The current flowing year over year. Okay, this is IB and this is IC. Okay, and this is our fixed bias circuit. So for fixed bias circuit, we need to do the following. First, we need to find Q point. What do you mean by it? Q point means we need to find the expression for VCEQ and IC. If it is a numerical, we need to find numerical value of VCEQ and ICQ. Second, find stability factor. So this is my second objective. Find stability factor. We call it S or SICO. Third, plot Q point on DC load line. We need to plot Q point on the DC load line. So these are my three main objectives for a fixed bias circuit, which is shown over here. Okay. Can I begin with the analysis, everyone? Hello. You've completed this much? Please give me a quick reply. Completed? Yes or no? Hello.
Yes, sir.
Okay, great. Now let's first focus on the first objective. That is to find Q point. That is to find VCQ expression and ICQ expression. So for that, we need to draw the diagram again. You have already drawn, so you all can rest. Let me draw it once. So this is plus VCC, right? This is RC, RB, and ground. Okay. Now, for finding the Q point, we need to apply KVL to the input loop and output loop. So if we apply the KVL to the input loop, let me mark this over here. This supply voltage is nothing but like this. This I'm doing only for the first circuit. I'll not do it again. This is VCC actually. Yes or no? So what is my input circuit? I'm highlighting with yellow color. My supply voltage, my RB, my base to emitter. This is my input circuit. Are you understanding? So let me mark these points over here. This is actually base current flows into this resistor, into the terminal, and then we have VB over here. I hope you're understanding. This is collector terminal, this is base terminal, and this is emitter terminal. So this is my input circuit, input loop, we can say. Okay. So first step is step number 1, apply KVL to input loop. So we'll start from here, right? We start from here. This is my loop. And we go till ground. Okay, like this. Are you understanding? So tell me how we'll start. This is minus plus. So do we write this is VCC? Then you have IB RB. So it will be minus IB RB. Then you have VB. So plus minus. So it's fall in potential. So minus VB is equal to 0. Did you understand how I got this expression? Everyone, how do I apply the KVL? Yes or no? Simple yes or no. Give me fast. Hello? Understood how we have applied the KVL? We started from here. It's minus plus rise in potential, so VCC. Then we are going over here, there is a voltage drop ICRC, and then we have VPE equal to 0. Did you understand this? Yes or no? This is my input loop, entire thing. Okay. So here, let me just take this aside on the right hand side, left hand side, and rest everything over here. Okay, this is what we get. So how much is IBQ? IB is how much? VCC minus VBE upon RB. Now, since we are following the Q point, that's why we write it IBQ. So this is how we find IBQ. And now anyone can tell me how we'll find ICQ or IC from IB. So they have a relation, IC is beta times IB. Yes or no? So can you tell me what will be the expression? Acha, before that, why this is called as a fixed bias circuit? Let us understand. Normally this VB is actually VB on, and this typically voltage is around 0.7 volt. Yes or no? VCC value is around, let's say 10 volt. It's a fixed value. It will not change throughout. And resistor value RB is also fixed. It will not change. And as you can see over here, VCC is very much greater compared to VB, even if VB changes. So your new expression will be IBQ will be approximately equal to VCC upon RB. And among this, both are fixed. This is fixed. This is also fixed. Hence the name fixed bias. Okay. Hence the name fixed bias circuit. Are you understanding? Yes or no? Now we want to find ICQ because that is the Q point. So how will you find ICQ from IBQ? So ICQ will be beta times IBQ, which is equal to beta times VCC minus VBE upon RB. So that's how you find ICQ. So this is first expression. This is expression number 2. Did you all understand this? Please write it and complete it. Please do it fast. Completed? Yes, no. Yeah. So we have so far, we are finding the Q point. We have found out ICQ. Now we have to go for VCQ. So for VCQ, we'll apply the KVL to the output loop. So let's write down step number 2. Step number 2 will be apply KVL to output loop. Now for that, I have to draw the circuit again. For y'all, it's already there. So this was my circuit. And we are applying only single power supply, VCC. This was RB, this is RC. Okay. Now where is my output loop? Basically, this power supply is connected like this. I'm drawing in different colors so that you don't have to draw this. You have to understand that from now onwards, it will be like this. Here it is, the power supply, and this is other terminal is ground. This is VCC. Okay. And what does the current flows through RC? IC. And what are the terminal voltages over here? Plus minus VCE. So I'm highlighting the output loop. It starts from here, goes into the collector terminal, then the collector resistor, out of this thing, and then over here. So this is my output loop. And this is the way we apply KVL. So tell me, we're starting from here. We are going from minus to plus. What do we write over there? Plus VCC, correct? Then it will be minus ICRC. Then plus minus. So fall in potential. So minus VCE is equal to 0. So how much is VCE? VCC minus IC, RC. But since we are finding the Q point, this will be VCQ, this will be ICQ. Got it? So this is my expression for VCQ. We call it expression number 3. Did you all understand how to find this by applying KVL to the output loop? Yes or no? If you have any doubt, you can ask me. I'll stop and explain again, no problem. But tell me fast. Tell me quickly. Okay. So step number 3 will be actually writing the Q point. So Q point will be VCQ. Now we have the expression and ICQ. Understood this? So this is finally my Q point. Okay. So this is how you find Q point expression of ICQ over here and then VCQ over here. This we have to do it for remaining biasing circuits also. Now, let's go to the second objective. This was the first one, right? A. Let's go to B to find stability factor S. Okay. Now, what was the expression for S we have derived? 1 plus beta divided by 1 minus beta times delta IB upon delta IC. Yes or no? Correct or no? So from this expression, we have the value of beta. We can write beta, but delta IB upon delta IC expression we have to determine. So we'll again write the expression KVL to the input loop. We have already done that. So we'll directly write the expression over here. So KVL to the input loops will give you this. VCC, this one. Let me highlight in yellow. This expression. VCC minus IBRB minus VB. So let me write this. So this is the input loop which we are applying. Let me quickly draw it and show it to you. This is plus VCC, RB, RC. See this. We are applying the KVL over here in this loop like this. This is plus minus VB. So what was the expression? VCC minus your IB flows, IB RB minus VB is equal to 0. Okay. Now this expression we differentiate with respect to IC. So differentiate with respect to IC, which will give VCC is a constant, so it will be 0 minus RB is a constant. So you will get delta IB upon delta IC. VB is a constant, we treat it as a constant for the analysis. So it will be equal to 0. So what does that mean? Delta IB upon delta IC is 0 for fixed bias circuit. So let's substitute this value over here. So what do we get? What was S given by 1 plus beta divided by 1 minus beta delta IB upon delta IC. And how much is this now? 0. So what will be the expression? 1 plus beta upon 1 minus 0. So finally, what is the expression for the stability factor? 1 plus beta. Here it is. And this is for fixed bias circuit. Fixed bias circuit. Okay. So what does the significance of this stability factor is? So let's say if beta is 100. Okay. So what is S? 101. Very, very high. That means if ICO, let's say the ICO value is around 100 nanoamperes. Okay. For example, changes by 1%, your IC will change by 101%. It's very, very bad. Okay. If IC, which is very, very small, it's a leakage current, right? It's supposed to be very small. Changes by 1%, your IC changes by 101%. So basically the stability of this circuit is very, very poor. So the stability of fixed bias, because IC should not change and it is changing by 101%. Therefore, the stability of fixed bias circuit is very poor, very, very poor. Okay. Now the last part, that is, understood this, everyone? Are you following? Yes or no? We have derived now the stability factor for the fixed bias circuit. Okay. Now we'll go to the third objective, that is plotting of DC load line and locating Q point on it. So let's do that. Objective number 3, plotting of DC load line and locating Q point on it. Okay. Now, what is, let me prepare my x-axis and y-axis. This is IC, this is VCE. So this quantity is associated with y, this is x. Okay, that much you can know. Okay, so load line, first we'll write the load line equation. So load line equation is nothing but KVL to the output loop. So KVL to the output loop, we have already have the expression, right? What was the expression? Here it is. KVL to the output loops gives me VCC minus ICRC minus VC equal to 0, right? Here it is. So let me write that again. So it's VCC minus ICRC minus VCE is equal to 0. Correct? Let me call this equation number A. Now we can write ICRC is equal to VCC minus VCE. Is it right? Now we can write IC is equal to minus VCE upon RC plus VCC upon RC. So this is my expression for IC. Now, do you know the mathematical expression for a straight line? Y is equal to mx plus c. Okay. What is m? M is slope. And what is c? Anyone can tell me? C is the y-intercept. Yes or no? And what is y actually in our case? In our case, y is IC. Yes or no? What is x? VC. So can you correlate these two equations and can you tell me what is m? Come on. This is y. This is x. What is m? Slope m is minus 1 upon RC. And what is y-intercept c? VCC upon RC. Can you correlate these two now? Y is equal to mx plus c. So basically this is indeed the expression of or equation of DC load line. Now we got the expression of a DC load line. How to plot the DC load line? Okay, so we have to plot it over here, right? Or let me redraw it over here. We need to plot a line over here. So to plot the line, how many points we require? So to plot a straight line, we require two coordinates. Yes or no? So let's say I have two coordinates, one over here, one over here. Can I draw a line over here? Yes. So to draw a straight line, I require two coordinates. So let me rewrite the load line equation. So load line equation, the output equation is given by VCC minus ICRC minus VCE is equal to 0. So in the above expression, in the first case, I put IC equal to 0. So if I put IC equal to 0, what will be VCE? Come on, tell me. If IC is equal to 0, VC will be equal to VCC. Yes or no? So my first coordinate or my first point will be VCC comma 0. Yes, because IC is associated with y-axis. This is x-axis. Secondly, we'll put VCE equal to 0. When we put VCE is equal to 0, you will get VCC minus ICRC is equal to 0. So what is IC now? VCC upon RC. So my second coordinate will be, second point will be 0 comma VCC upon RC. Okay. So we need to plot these points on the graph. Are you understanding how we are finding these points and why are we plotting we are plotting the DC load line? Are you following? Yes or no? Hello. Yeah. So let's plot the point now. So this is my graph, output graph. This is VCE. This is IC. Acha, where is my coordinate VCC comma 0? Let's say over here, VCC comma 0. This is first point. This is the first point. Second point is 0 comma VCC upon RC. Remember, VCC upon RC is a current. So it will come over here. Let's say over here. So this point will be 0 comma VCC upon RC. So 0 comma current, and this will be on the x-axis, this will be on the y-axis. Now we have 2 points. So join them to get a straight line. So when we join them to get a straight line, this becomes my DC load line. Got it? Yes. And when we plot the characteristics, when we finally plot the characteristics, this is the output characteristics, right? The intersection of DC load line and the output characteristics will give us the Q point, and which is nothing but VCEQ and ICQ. And do we have the expressions for them? Yes. So again, I am repeating, intersection of DC load line with the output characteristics is the Q point. Okay. So Q point, I've already told you all what are the other names for the Q point: operating point, or quotient point, or a quiet point. It should not change. Again, I'm repeating, operating point or quotient point, silent point. Okay. What does the Q point will guarantee? The Q point will guarantee, this is most important learning from today's lecture. The Q point guarantees that BJT is only operating in active region, of our active region, which we call it. It should operate only in the active region. So this will guarantee that. Okay. Everyone understood? Yes or no? Are you all following? Yes or no? Can you all reply, please? Because I have been continuously speaking for a long time and there is a quiet on your side. You all are following the topics. I'm not getting the feedback.
Yes.
So you have completed up till
Yes.
here? Hello? Completed up till here? Yes or no?
Sir, could you scroll up for a second?
Now better?
Yes, sir. Thank you.
Now please remove your calculators. Just 5 minutes more. We'll complete one numerical and then we'll rest for today's topic. We'll solve our first numerical of this for analog electronic circuits. Completed? Okay. So now let's solve numerical number 1. It should take 10 minutes more. Numerical number 1, write down for the circuit shown below. Circuit shown below, find ICQ, VCEQ, stability factor S, VB, VC, and VBC. Also comment on region of operation. Okay. So what is my circuit given to you? Please draw the circuit. This is RB, this is RC plus VCC. Now the values given are VCC value is around 10 volt, RC value is 3 kilo ohm, RB value is 500 kilo ohm. All right. Now for a BJT parameters are, the following parameters should be known to you: VB, E, and beta. So normally VB value is around 0.7. You can assume it also. So we can assume, if the data is not given, VBE is 0.7. Okay. What about beta? Beta should be given. So beta for the circuit is 100. If beta is not given, you can ask for, or you can assume the value to be 100. Okay. So these are the values given. Now we have to determine IB, IC is flowing over here in this. We have just now done the analysis, right? Achha, anyone knows what is kilo ohms? 10 raised to 3 ohms. Yes or no? So if I write 1 kilo ohms, does that mean 1000 ohms? Yes. Correct? Are you all ready? Have you completed this much? Can we start solving? So let's write down the solution. So first we apply KVL to input loop. So we have already done that, right? KVL to the input loop is from year to year. So it's VCC minus IBRB minus VB. We have done the analysis, so I'm writing it directly. It's VCC minus IBRB minus VBE is equal to 0. So what is the expression for IPQ? VCC minus VBE upon RB. So how much is VCC? 10 volt. How much is VB? We have assumed 0.7. How much is RB? 500 kilo ohms. I'll give you one hint today. Very, very crucial thing. The range of IP, the value will always come in microamperes. Huh? Always remember, if you're getting other than that, that means you're doing something wrong. So please tell me the value of IBQ. How much it is? It will be 9.3 upon 500 kilo ohms. 500 kilo ohms means 500 into 10 raised to 3. How much is the value of IBQ? Come on, tell me fast. It will be in microamperes. Tell me in microamperes. Microamperes means 10 raised to minus 6 amperes. What are you getting in your calculators?
0.2.
Tell me in microamperes. No, 0.2, no. It will be 9.3 divided by 500K. Na? Don't approximate. Anyone else?
So then it is 0.186 into 10 raised to minus 6.
0 point
186.
Into 10 raised to minus 6. No, it cannot be. Type that properly. 500 into 10 raised to 3. 9.3 divided by 500 into 10 raised to 3. Can you tell me again, anyone else? Anybody? Proper value of IBQ is how much? It should be around 18.6. Are someone getting 18.6 microamperes? So you should get 18.6 into 10 raised to minus 6 in your calculators. Students, please let me know. How will I get to know whether you are getting the answer or no? Please respond. Are you getting
Yes, sir, got the
18.6?
answer. Yes, sir.
It's 18.6. So this is the first step. Second is calculate ICQ. ICQ will be beta times IBQ, which will be into 100 into 18.6 into 10 raised to minus 6. So tell me ICQ now. This will be 1.86 milliampere. Remember, ICQ will always come in milliamperes. This will always be in milliamperes. Are you getting 1.86 now? Multiplied by 100. Yeah. So milliamperes will be 10 raised to minus 3 amperes. 1.6 are you all getting? Yes, no. Hello. Are you all getting this much? Okay, I'll go ahead assuming that you've already got it. So now the third thing will be to apply KVL to the output loop. My output loop over here is this. Let me use a different color, the green one, like this here. So over here, I'll mark plus minus VCE. Yes, if I make it clear over here, let me do it over here so that to avoid confusion. I'm only interested up till here. That's it. I'm not interested here. So this is my output loop. This is my current IC, sorry. This is my voltage VCE, and I'm applying my uh, output loop is this, right? So how do you write this expression? VCC minus ICRC minus VCE is equal to 0. So how much is VCE? Q now. VCC minus ICQ into RC. Calculate this number. VCC is 10 volt. ICQ you got it as 1.86 milliampere, that is 10 raised to minus 3. RC is how much? 3 kilo ohm, right? So 3 into 10 raised to 3. Please let me know the answer of VCQ. Do it in your calculator carefully. Quickly tell. This and this will get cancelled. Very easy. 10 minus 1.86 into 3. Is that 4.42? Anyone getting 4.42? Yes or no? Please tell me.
Yes, sir.
Next will be stability factor, which is 1 plus beta, which is very simple, 1 plus 100. That will be 101. Next, I have to calculate, let me check, VB, VC and VBC. So let me draw circuits for you again. This is for your understanding. I'm drawing it again and again. This is VCC. This is RC, RB. Okay. Now, which are the terminals over here? This is the base terminal. This is the collector. and this is the emitter. Correct? Now, what are they asking you to find out? VB. VB, right? VB with respect to ground. So how much is VB with respect to ground? It is same as VB. So let me write. VBE is VB minus VE. VE voltage is zero. Emitter voltage is zero, no? If you check emitter voltage over here, this point, okay, with respect to ground. So this is VE, right? It is zero because emitter terminal is directly connected to ground. So this is zero. So VB will be equal to VB. So how much is VB then? 0.7. Agree? Yes or no? How much is VC? See, VC is this. Okay. Now again, same analysis. VCE is VC minus VE. This is zero. So how much is VC equal to? VCE, which is equal to, we have already determined that 4.42. Are you understanding? Yes or no? And how much is VBC? VBC is VB minus VC. How much is VB minus VC? This is, how much is that? 0.7 minus 4.42. VBC is how much? Minus 3.72. Yes or no? And we have to determine the comment on the region of operation, right? We need to comment on the region of operation. So what do you say about the region of operation? See, base emitter junction is forward bias. That is, we have assumed. From where do you get this information? From VB. Since VB is 0.7, it is forward bias. What about the base collector junction? Negative, na? So negative means is reverse bias. So in which region of operation my device is? Anyone? Base emitter is forward bias, base collector is reverse bias. So BJT is in active region. Are you following? So please have a look at it. Okay. Everyone followed this? And you got all the values as we are getting over here. So what are the important values over here? We have VCE, ICS, VB, VC, VBC. So if we have completed this, let's finally plot the DC load line. So DC load line, already we have seen the how the DC load line should be. I mean, the plot the Q point on the this thing. So let's do it. This is IC. This is VCE. What are the two coordinates of the Q point? Anyone can tell me? VCC, comma, coordinates of the DC load line, VCC, comma 0. So this will be how much? In our numerical 10 volts, comma 0, right? And this is how much? 0, comma VCC upon RC. Can you calculate VCC upon RC? How much it is? 10 volt divided by 3 kilo. Quickly tell me. It will be a current. So what is this number? I think 0, 3.33 milliamperes, right? If I'm not mistaken. So now you have 2 points. Connect them to join a line. So here is my line. So this is my DC load line. Now how will I plot the Q point? Q point we already have the value now. What is VCQ around? How much it is? We have found out now how much it is. 4.42 volt. And correspondingly, how much is the value of ICQ? Come on, tell me from your numerical only. ICQ was 1.86 milliampere. So it all makes sense now. See, you join this on the line. So Q point will be on the DC load line. So this is my Q point and this is my DC load line. Okay, so this is how this is how we plot the actual Q point for a circuit with numbers. Understood the gist of it? The IC value is in milliamperes. So this is 0, 3.33. It makes sense. It's a higher value. This will be lower than that, 1.86. This is 0 to 10. So it's coming in almost the midway. So this is all makes sense. The values are all fine. So this is how we solve a numerical on a DC biasing circuits. So that is we end over here. Just wait. I've stopped the recording.